So let's talk about containerizing a Qt embedded application. First of all, let's start talking about containers. And I think for this presentation, it's easier to start about containers in the real world. So if we need to define a container in the real world, probably we can say it's a metal box. It's usually quite colorful. It has some logos, but apart from this, they really all look the same. They are kind of boring things. Probably this guy didn't agree with this. Is Michael McLean, and actually is credited to be the inventor of containers, or at least the man that make this idea very, very popular. He used to have a transportation company in the US in the 50s, and basically, he wanted to improve the efficiency of transportation between trucks and ships. The company was named Sealand. And the first idea was to put the trucks on a ship and move them on the sea. But this was not very efficient because, of course, trucks themselves were taking some space and so on. So next step was to put this big metal box on a truck and then remove it and put it on a ship. And that was definitely much more efficient. It started in the 50s and struggled a bit at the beginning, but this idea became very popular in the 60s, also due to the Vietnam War, because the US had to move a lot of stuff to Asia. And this opened new route from the West Coast to Asia, together with the routes that were already in place between the East Coast and Europe. So transportation over containers became very, very popular. And the main reason, it's basically cost. So loading a traditional ship at that time was costing like $6 per ton. And with containers, it was costing just 16 cents. So containers were definitely very optimized solution for the problem of transporting many kind of goods. Not everything. We still have dedicated ships and transportation for some specific things, but they became very, very popular. What are the advantages about using a container? The container is a standard package. The shape and size of each container, it's well defined. And as I said at the beginning, from the outside, apart from the color and the logos, they really all look the same. And this means that we can have a shared infrastructure. We can have cranes, we can have dockyards, we can have trains and trucks that can host containers, and basically without caring much about what's inside. We can move this stuff around in the same way. It's containing chips, it's containing food, it's containing whatever. We can rely on the standardization to handle them more or less in the same way. And this is what really made the difference, because in the past, each and every kind of good that had to be transported had dedicated boxes and dedicated different shapes and sizes. And this made really loading and unloading stuff on a vehicle, ship, train, or truck quite a complex thing. And also containers are quite versatile because they can be used on ships. This is probably what is really moving the biggest amount of goods, but then you can also move them on a truck or a train and really get closer to the final destination of your goods. And really, container change completely global trade over time. Probably I didn't took the best sample for the picture, but yeah, the point is really even what happened just a few days ago with ship in the Suez Canal shows how important transportation is for the global economy, and ship-based transportation too. And a good percentage of the goods moved around by ships are actually moved into a container. So container, it's really not a technology. I mean, I wouldn't say that. It's, I mean, boxes that have been around for centuries, but it's really the idea of standardizing some things to make these boxes much easier to move around and load on different kind of vehicles. Okay, so how does this relate to software? We are supposed to be talking about software in this session. So let's move forward. When we think about containers in software, we can define a container as a way to package our software in a standard and easy to deploy way. So in the same way, we can put our physical goods inside a metal box named container. We can take our software and package it in a container that really looks the same from the outside, not depending much about what we plan to run inside it. This means that we have a standard package, and this also solves a kind of a long-standing issue of the software industry. Probably each and every developer has said this sentence at least once in his lifetime. It works on my machine. With a container, you can ship your machine. So your software is going to work in the same way in different scenarios. Of course, you're not really shipping your machine with everything, but you can create an environment where your software is going to be running in the same way on different systems. So you are not relying too much on the underlying system. You need a container runtime and some services, but you can really create the runtime environment for your software application. How do you define this? You define this using a Docker file. Probably some of the people in the audience already use container, already know about Docker. But that's just to give a quick introduction to those who never use this kind of technology. In the Docker file, basically you define from where do you want to start, and usually this is a base image. You can even start from scratch, and you can provide a complete file system, but usually you start from a distribution. As you can see here, I'm starting from Debian, from a specific version that is Bullseye, and from a specific let's say, configuration of this version that's Slim. And it's really a configuration that is designed to run inside a container. It's not containing all the services and stuff that you usually start at boot with a regular distribution, because we don't need to boot to run in a container. So it's reducing footprint, and it's providing just a minimal set of libraries and features. Then we can just execute some command as we would execute them directly on the console of a Linux system. For example, since this is Debian, we are going to use apt for the packages. We are going to install some packages. We can also copy some files or contents from the local machine to the container, to a specific location. And at the end, with CMD, we can basically tell the system which process do we need to start when we create and start the container. By default, we can start one process, of course, by running a script or something like this. We can also spawn multiple ones. This idea of the container, that it's, let's say, standardized from the outside, allows us also to use a common infrastructure. As we have been talking before about cranes and dockyards and so on. We can have common tools to build our container, as we have seen with the Docker file. We also have a container runtime that can run containers, and again, without caring much about what's inside them. It's the same thing. And we can also have a container registry that is basically a repo where we can store all our containers, the different versions, and so on. So we can have also a share source for our containers. And as containers can be loaded on ships, trains, and trucks, also software containers can be run on servers, in the cloud, on developer machines, and why not, even on devices. Say container on devices, does this make sense? Yeah, I think it does, even if doesn't make sense to put a container on a small ship, as in this picture. We shouldn't think about our devices as small servers or something like this, or at least in software, they are not so small. One important point is that containers are designed to be efficient. Efficiency is really a key point of the container concept. And one common misconception is basically associating containers and virtual machines. When we talk about containers, we are not talking about a virtual machine. We can probably use the term like kind of lightweight virtual machine or user mode virtualization, but there are quite some differences. This is, as I said, a common misconception. For example, if you used to build your embedded Linux images using Yocto, the layer where the containers runtimes are stored is named meta virtualization. But it's really not virtualization. So let's see in detail. This is the architecture diagram of any Linux system, like my PC that it's now used to run this presentation. In a common Linux system, we have multiple processes. They are running side by side, but they are isolated by the OS itself. They have a common file system, and through this file system, to entries like /dev or /proc, they can talk with the kernel. They can also, of course, use APIs to call the kernel directly. And the kernel, it's there, it's running directly on top of the hardware. It's exposing the feature of the underlying hardware through a device driver model and so on. So we can take this model and encapsulate it inside the virtual machine. We can then run multiple virtual machines side by side. We can even run different operating systems, different versions of the same operating system, and so on. This can be very convenient if we have quite powerful hardware. And I say we need quite some powerful hardware because to be able to really implement this virtual machine concept, we need some support on the hardware side and also some software underneath. I called it hypervisor in this 20,000 feet architecture diagram. You may see different terminology, but the concept is that I need some software that makes the kernel believe that it's running on real hardware, but then it's taking the request that the kernel is making to this hardware and translate them to the actual hardware underneath, and also keep all the virtual machines separated one from the other. This adds quite some overhead. On a server, it's probably kind of a price you are willing to pay to keep running different things completely separated and so on. On a small device, this may be too much overhead for many kinds of applications. When we think about containers, you see the schema, we are not talking about a virtual machine. We don't have anything around this. This is our kernel. It's happily running directly on top of the hardware. We don't have any kind of hardware virtualization there. And on top of this, we can run processes directly, as we did in the first architecture diagram, or we can create this kind of sandbox that we call a container. And inside this sandbox, we can run other processes that have a different view of the file system. So the main difference between running directly on top of the OS or inside the container is that we have a different view of the system underneath, but we are talking with the same kernel. So this means that a call from this process or a call from this process are going through the same layers, and probably at the end, or without probably, at the end, they are going to have the same performances. The containerization, it's really not impacting runtime performances. Of course, when we need to create the container, set it up, we need to leverage some features in the kernel, namespaces, cgroups, and so on. So this may add some time, some overhead to the startup time, but not at runtime. So yeah, the idea is that the container, it's a sandbox when we take an application or a service and run it inside a well-defined environment. The idea of shipping our machine, as I said at the beginning, it's really connected to this. So we can take our software and all its user mode dependencies, put them together, and always run it in the same way in different scenarios. What can be the disadvantages of this architecture? Of course, we don't have the hypervisor, so we don't have this runtime overhead, but we still need a runtime that it's needed to set up the environment to run the container. And this runtime definitely has some footprint. And since we keep multiple copies multiple different file systems, this also requires some storage and some memory. So definitely when we run software in containers, we probably need a bit more storage, a bit more memory bit, or much more. Really depends on the specific scenario we are thinking about. But since containers are about efficiency, also in this aspect, the container runtimes usually try to help us reducing this footprint. One good idea in containers are layers. When we think about a container or a container image, the easiest, let's say, mental model we can build, it's just an archive. So we have an archive with our file system, and then when we run, we kind of unzip, untar our archive and run it. But this is actually not what's happening. For example, if we think about my presentation, the one that was supposed to be running at the beginning, in this presentation, I have a container image, but actually in the container image itself, I have only my slides, that is HTML, and some images, and configuration file for Nginx. That is a quite popular web service, a web server, and that it's used because it's quite small, quite efficient. And inside my image, my specific image, I have a reference to the Nginx image. In the Nginx image, I have other layers with the Nginx binaries and the Nginx configuration file. And probably the Nginx image itself, it's again pointing to another image on top, the one we identified with from in the Docker file, that it's containing the base distribution and so on. So by keeping stuff separated into those layers, we can share some layers. If we are running multiple containers based on the same base distribution, definitely we are going to do this. And so we need to store the layers of the base distribution only once. That's already reducing the footprint. Talking about reducing memory usage at runtime, the Linux kernel is smart enough to understand that when we try to load the library from a layer that is shared between different containers, if we try to load it from two different containers, it's allocating the memory only once. Same way that if we are loading the library across two different processes. So the system is trying to minimize really the downsides. What are the advantages of distributing our applications as container? We can basically pack our application and all its user mode dependencies inside a single package, as I said before, standardized package. We can also limit interdependencies. What does this mean? We can build a nice embedded devices with a Qt application, with a web server implemented maybe with Python or Nginx or Node.js, and so on. We bundle everything together. We need to do some effort to do this with Yocto, with Buildroot, whatever. And we have a very efficient, very small image. But then we have lots of interdependencies. At some point, we may need to update the web server because there is a vulnerability that has been discovered. But this means that we need to update the library, that needs another library, that needs another library that is needed by the main application. So a small security patch is becoming a major update. With containers, we can really split the different, let's say, parts of our system in kind of microservices or anyway, a kind of distributed architecture. And in this way, we can have different release cycles for the different components once we define the way they can communicate to each other. For example, I can move part of my application to Qt 6 and keep other parts to Qt 5. I can do this within an integrated image. This is definitely more complicated. We can also leverage modern toolset technology. A lot of runtimes are available as containers. So the focus here, and that's the last point, it's really to let you focus more on your application, on your system, or what you need to provide the features that your users are asking for, rather than the operating system itself. But then why we don't just use the distribution? Also using a distribution, we already have a set of components. We can update individual ones. Issues that distribution are really not optimized for embedded devices. Debian or Alpine or Red Hat or something like this are really not designed to run on embedded devices. They are designed to provide a desktop or a server environment. There have been, over time, some distribution targeting embedded, but honestly, then the number of packages compared to Debian or the others, it's quite small. So the advantage of running a distribution was quite relative. Also, many of those distributions provide a way to update the packages, but they don't provide fail-safe updates or these kind of things that are usually critical for an embedded device. And again, since they are designed to kind of desktop usage or server usage, even if they are targeting small devices like a Raspberry Pi or something like this, they are really not optimized for the resource usage we may want on a small embedded device. And this is some kind of advertising for Toradex, sorry for this, but it fits with the concept also. What we do is to provide a small operating system. It's built using Yocto and Open Embedded. It's fully open source, so you can look into it. That provides kind of the base, a solid embedded Linux Linux-based operating system. And on top of this, we allow you to run containers for your application. So you are free to use a distribution to build your application. And we also provide support for over-the-air update. But if you are interested into this specifically, you can go on our website and you will find plenty of information. But this is also what I'm going to use for the demos and so on. So made sense to introduce this concept. We are running containers on embedded. I hope that the first part of the presentation was useful to make you understand why and when it makes sense to do this. It's possible to do this, definitely. I'm not saying that that's the only way to run software on an embedded device. That's not true. You can still use Yocto, Open Embedded, build root, anything you want. As operating system never fully replace firmware, I think containers are not going to fully replace dedicated build of an embedded Linux system. As shipping containers never fully replace custom-made ships for some kind of goods. There are so many different scenarios that this architecture may not match your requirements. I perfectly understand this. But on the other side, I'm trying to, let's say, tease you to really try it and try to figure out if it can fit your scenario. Because if it does, you can get some benefits in terms of ease of development of your software and long-term maintenance. But since we work in embedded, we also have some embedded specific requirements that are definitely not common to what happens when you're running containers on a server or in the cloud. The first one is hardware access. We are going to talk about this later. We will also need to think about how our system starts. And probably we also need to talk with the underlying OS in some scenarios. Let's try to address these different requirements. First of all, let's talk about startup. Bad news first. Using containers is probably impacting startup time. If your goal is really to boot in under less than 1 second or a couple of seconds, depending on the hardware you have, initializing the container runtime and creating the, let's say, sandbox environment to run your containers is probably taking some time. So it's impacting the overall boot time. So devices that have a very short boot time probably are a scenario where containers nowadays don't apply too well. But to give you an example, with Horizon, we boot in 20-30 seconds, depending on the hardware architecture. And honestly, we didn't spend too much time optimizing this. So if this kind of boot time is reasonable for your kind of devices, then probably you can safely use containers. We also need to start multiple services when our system boots. And this is definitely a challenge. We need to start them in the right order and so on. But for this, we have a tool that is named Docker Compose that solves the issue. So that's the good news in this slide. Another step, it's hardware access. We need, the idea is that the container is a sandbox, so it's isolating our software from the underlying hardware. And this is probably what you want to do when you're running software on a server or in a cloud environment. But on a device, at some point, the let's say, features of an embedded device are really coming from the integration between hardware and software. So your software at some point needs to talk with some physical hardware. And since it's running in the sandbox, this may not be possible by default. But the good news is that the container runtimes, Docker or others, give us ways to kind of dig holes into our sandbox. So we can expose devices inside the container. And this usually happens by sharing parts of the host file system. The Unix mantra is everything is a file, and basically by sharing some virtual files inside the container, we can get access to the hardware. So it's not possible by default. We can enable this. This means that by default, your software is running in a quite secure environment, and you can, let's say, give it access to what it really needs for specific purposes. Another good effect of the container runtime is that you can limit resource usage. So, for example, you can limit the amount of CPU and memory and the I/O bandwidth that a container can use. And if a component of your system is buggy or it's subject to a malicious attack, and it's like allocating memory without releasing it, or it's using a lot of CPU, you can still keep this usage under a certain limit and prevent it from like using all the memory, or prevent a more critical part of the system from running. So that's also a good way to use the container runtime to make your whole system a bit more reliable. When we talk about hardware access, definitely a topic is graphics or user interface. Here we need to access the display controller, the GPU if you have one, input devices, and so on. We can use Wayland or we can use X11. Honestly, on Horizon we use Wayland because this is what's supported by the more modern SoCs. You can also do the same with X11 with some performance impact due to X11 itself, not to the containerization. What you need to do to access this kind of graphic, let's say, servers, even if in Wayland it's called Compositor, is to share a socket as kind of connectivity between the client and the server, and you can easily do this with container. Both systems have a kind of client-server architecture. With Wayland, you also may want to share memory or something like this, and this is also you can do across container boundaries. Of course, it's something you need to do explicitly. It's not happening by default, but once you do it, it's working. So it's working as if you're running processes on top of the same, on top of the OS directly. I mentioned Docker Compose. Let's quickly see a Docker Compose file. Here we have a version. And then in a Docker Compose file, we define services. This is what I used to run a Qt application, a Qt demo actually, on our devices. We have two services. One is Weston, that is the Wayland Compositor, the equivalent of the X server if you are coming from X11. And here we have our demo application. As you can see here, we reference an image. We already provide the image for Weston, so you don't have to build it. You can define some environment. We also bind mount some part of the host file system inside the container. And we need to bind mount /dev and run udev because this container need to be able to access to some hardware devices, display controller, GPU, and so on, and also need to be able to detect devices that are connected at runtime. So if I plug a mouse or keyboard, it's able to manage this without having to restart it. Sometimes you need to enable some additional capabilities. For example, this container can reconfigure a TTY, that is the one on the screen, because it can change resolution and so on. And we can also enable it to access some specific devices identified by their major number. In this case, it's TTYs, it's input devices, it's graphic rendering system, and graphic acceleration. And then I have an application. I hope to be able to show it later. And this application, it's also coming from a container image. It also has access to some devices, less than Western, but still it needs to access the GPU, because in this application we are going to use graphic acceleration, and to do this you need to access the GPU. But as you can see, those two containers are accessing some hardware, but also this access is limited. They are not accessing like the eMMC, so they are able to erase all my data or something like this. And also here we have some bind mounts. Let me see if my device now it's reacting better than before. I hope so. Let me share the screen. You can see it here. I'm trying to start the same Docker Compose file I've been showing. Okay, now it works. Okay, and you can see here, this is a quite popular demo from Qt. Probably you have seen it. I can also show that it works. I have a super small keyboard, so interacting with the screen, it's a bit clumsy. Also because I'm watching the screen, as you can see it on the in the session, so I have some delay, and using the mouse with some delay, it's really crazy. But yeah, you see it's working. I have the frame per second counter. I promise I didn't cheat about this. So it's actually the same one of the demo. So you can see you can run a graphical application using 3D with the same performances as has been running locally. Okay, we have 10 more minutes, so I'm trying to speed up a little bit. Let me switch back to the presentation. There are other scenarios where we want to access the host system. First of all, we may want to store some data permanently. It's not a good idea to store data inside the container, because the container can be stopped and updated and restarted and so on. But it's pretty easy to share, as we have seen already, parts of the local file system inside the container. And of course, if you share the temp folder, this is going to be just in memory. But if you share a folder that it's matched by some kind of storage, you can permanently store your data. You can also share this data between different containers. By sharing the dbus socket, at least in Horizon, we use systemd that it's usually is using heavily dbus. With dbus, you can perform a lot of configuration on the underlying system. Because, for example, you may want to change the IP address of your device. You can do this from inside the container. You are sandboxed, but you can do this using dbus. Or you can, for example, switch from static IP to DHCP and all this kind of operations. We have some samples on our website about how to do this. Another thing you can do is reboot your system. Or you can share the Docker socket or the container runtime socket. And since all processes can talk with Docker in this way, you can run the Docker client or Docker APIs inside another container. So you can have a container that controls the others and, for example, works as a kind of supervisor in your system, checking that everything is working correctly, stopping and starting different services, and so on. For example, Azure IoT Edge, it's really implemented in this way. You have an agent that it's loading, downloading, and starting and stopping containers depending on the configuration you keep on the cloud. So if in the cloud you decide to change your setup, the agent is aware of this and it's stopping and performing all the operation. And you can do this, you can run it inside the container in this way. Talking about development, we can use of course, any development tool we want to develop for containers. If you want to develop for Horizon, we have Visual Studio Code. It's officially supported. We have an extension. I'm going to show it quickly. Or you can use Qt Creator. We have some documentation on our website. You see the link here. Probably you're going to be able to download the slides later. And there you can find some documentation about how you can configure Qt Creator. I'm going to just quickly show you how can be development on such a system. Here I have Visual Studio Code. This is an application named Cydia Studio. It's an open source application. It's Qt based. We wanted just to show something a bit more complex, just a small demo, a small sample. You can take it, and with our extension, you can build it for our device. The build system is running inside a container itself on your development machine. We are getting a bit pathologic about containers there, but it works. Since you're running inside the development container, you can run this on a Windows machine, on a Linux machine. That's the same, and you have the same behavior. And you can use this to build your application with Qt, and then it's just a matter of pressing F5. Let me share the screen of my device. This is going to start the application and deploy it on the target, and then I can debug it and look into it. See, now it's starting the container. You see there is some time for this operation, but now if I switch to the debug console, you see here it's already initializing Qt. Of course, Qt, it's loading quite some stuff at the beginning, but after a few seconds, we will end up in the first instruction of our code. So you can, from there, you can start debugging your application like step by step, or checking what's going on, the values of the different things. You can have all the typical bell and whistles of an interactive debugger. Okay, so even if my application is running on a remote device inside the container, I can easily debug this on my machine. With our Visual Studio Code extension, it's really working out of the box. With Qt Creator, we have some documentation. There are some manual operations, so it's not as smooth as is in this demo, but you can still do it. Now I can start the application. I wanted to show it, but I think we are running short on time, so maybe I will come back later. And now the application is starting. You see all the libraries and think that it's loading. Of course, running through the debugger, it's also slowing down performances because we have all these interactions. But you see the application it's running. And now on the same device, I have two Qt applications running at the same time, sharing the screen, because the screen is managed by the third container, and they're running side by side. I can also have like a Qt 5, Qt 6 application running at the same time. They are completely independent. So if I do some changes here, I'm not impacting the other one. Okay, let me switch back to the presentation so we can quickly go to the end. What are the steps you need to do to containerize a Qt application? The first step is kind of optional, but I think it makes sense to use containers also for this step, and it's building. To build, you can create a build container with a cross-compiler. Inside this container, you can install and build Qt and use this to build your application. Why I say it makes sense to do it? Because first of all, you have, again, an environment that is well-defined. It's reproduced on different systems. So you can take this container and give it to your colleague, and it's going to have everything already set and up and running. So you don't have, let's say, mismatches due to the fact that I'm using a distribution, my colleague prefers another one, and so on. And also, this system makes it very easy to use it inside a CI/CD system, so you can do builds on the server, always in a well-defined environment. This is how you can define a build container. I'm using Debian, and here I think it makes sense to use Debian because Debian, it's really helping on this side. As you can see here, I'm using Debian Bullseye. I'm not using the slim version. This is going to run on a PC, so I can probably waste a few megabytes of space. I define my architecture. That's the Debian architecture. Unfortunately, they don't have very coherent name. It's ARM-HF or ARM64, and then you have the compiler prefix. Every person that tried to do cross-compiling knows about this prefix. We define some environment variable, but that's not very interesting. What's very interesting is that inside my container, I add an architecture. This is a feature that is specific for Debian, but it's very useful when you do cross-compiling, because by adding an architecture, you basically allow the system to install packages that are not for the native architecture. So in this system, I'm going to be able to install ArmyChef packages, even if it's x86. They are not compatible. They are not binaries I can run, but I can install the packages. And the usefulness of this came when I installed the cross-compiling toolchain. And I start to install packages, you see, with semicolon, ArmyChef. I can install packages for a different architecture. So the cross-compiling toolchain, it's able to get the right packages for the right architecture. I can install ArmyChef packages, and I have a cross-compiler environment set up immediately. I don't need to build stuff or stuff like this. I can still build Qt and maybe use this to install the base libraries needed by Qt if I need a custom version of Qt in my system. But I can really take existing libraries from Debian and use them in my container without having to do a lot of cross-compilation. And then, okay, I built my application. Now we need to run it. So we need to create a container, this time a container that it's able to run on the target device to host my application. We should run the services my application requires, for example, Weston, if it's a graphical application, and if it's a Qt application, probably there is quite a good chance of this. We need to define which devices we want to use inside it, and also define how we want to deploy our images. We can use Docker Hub, so a public registry. We can use a private registry. We can even take image and transfer them over SSH. So these are things that are probably depending on your specific scenario. But the way you can define the runtime container, it's going to be the same. Again, you can use different distribution. You can even build the whole file system from scratch with Yocto. It's possible. If you use Debian, you see I'm starting from Bullseye Slim, so the small version. And here I am installing all the different Qt libraries. Of course, again, probably you're going to select which packages you want to install. But with Debian, it's pretty easy. Qt, it's componentized in different, let's say, smaller components. So you can just go on packages.debian.org and select the set of components you need for your application. And of course, if you discover an issue, it's just a matter of adding the missing package here and rebuild the container and run it, and the issue should be fixed. If you build your version of Qt, then, of course, you don't need to perform this operation. You configure Qt at build time, but then you can take the Qt binaries and copy them inside the runtime container. And that's pretty much it. But OK, I skipped a small detail. We are building a container that is supposed to be run on a different architecture. And this is not supposed to be happening by default. But what we can do, we can use Beam format or QEMU. This is already enabled on Windows and macOS. If you use Linux, you need to check the documentation of your distro about Beam format so you can see how you can enable it. If you enable this, you can run binaries from for a different architecture using QEMU. And since Docker, it's basically running binaries when it creates a container. That's everything you need to be able to build it. One important thing, this is quite efficient if you're just using like the package manager. The package manager, it's really not such a big application. Most of the time it's spent downloading files and so on. So this can be quite efficient. It's not a good idea to run the full compilation in emulation because it can increase compilation time by 100 times. So it's good for just a small operation you perform to, let's say, build the environment, assembling it from packages is not good for complex builds. Another option that is relatively new, I think Docker has released it like 1 year ago, and it's enabled by default only in the latest versions, is to use BuildX. That is basically build cross-platform. If you use BuildX, then you can use just Docker build. That is the standard command to build a Docker file, and just specify the target platform, and the system is taking care of using the right images and so on. So you don't have to spend time on emulation. OK, I managed to stay in the timing, I hope. Is there someone from the organization telling me? Yeah, OK. If you have questions or...
Yeah, we have a couple questions. Thanks for the talk. That was great, very informative. So our first question comes from Chris. What about limited bandwidth when updating remote targets? connected via an unstable link. Is file size a problem?
I mean, also here, the layered organization of containers can help. Because if you're not changing the base layer, like the base distribution, that is probably the biggest component, but only lower layers, then also when you update the container, only this information is transferred. Each and every layer has a unique ID. So what's happening is the system is getting the full list of layers for your container image, and then checking, okay, I already have this one, I already have this one, I already have this one, I don't need to download it. So also this is efficient. Of course, downloading some kind of application over a small bandwidth link, it's still not pleasurable experience, but this can also reduce the bandwidth. And okay, some advertising. If you use Horizon, we also use OS 3 for OS update, so you don't need to download the full OS image every time. You just download the Delta, and this is also efficient. But this is definitely something you need to care about. If you have efficient connection, you can probably update the base distribution quite often. If you have this kind of slow link, then probably you should be careful, and you should design your system so you may not need every time to update the base distribution. If, for example, you need to update a library for a security issue, one solution can be update the base distribution. Usually they provide security updates. But for low bandwidth, better solution is to keep the old one and provide an additional layer with just the updated library, so you can ship a smaller update.
Makes sense. So next question. This idea is intriguing, but how much real-world adoption of this have you seen in actual projects so far?
That's a good question. I mean, first point is in embedded, you don't see stuff happening overnight. Usually, this is an industry that takes it time to adopt new technologies. There are some interesting solutions based on containers. I mentioned IoT Edge from Microsoft, Red Hat Fedora IoT. It's working using the same principle, so running applications in containers. There are other solutions like Balena IoT and so on that are using this architecture. There are probably already some devices out there, mostly in automotive, on this kind of application where security is critical, where this architecture is already used. And for example, just seeing that Docker has added specifically an option to compile container for a different architecture, it's really a sign that they are also looking into IoT, because they don't say embedded. Embedded doesn't sound so cool as IoT, but they're looking to IoT as a kind of possible scenario also for their tools.